Hello, this is Serena, and I'm gonna talk about how to use a reaction time strip to measure a human reaction time. The reaction time strip is actually like a ruler to measure human reaction time. This strip and test are actually based on the physical attributes of gravity. Thus, we know that by measuring the distance dropped, we can determine the reaction time of a person. The longer the distance, the slower the reaction times, and the shorter the distance, the faster the reaction time. Okay, now I'm gonna talk about how to make an RT strip first. Assuming that there are no air resistance, we know that in free fall, the distance fallen dy is equal to 1/2 times g times t squared, where t is the reaction time. From the equation above, we can figure out that the reaction time t is equal to square root of 2 times dy over g. Using this equation, we can calculate the reaction time T using Excel with known dy value. So, from this equation, we can calculate the time for the 5 mm increments using Excel. And we also have to note that the G will be 9.8 times 10 to the minus 3 millimeter per millisecond, because in here I want to use millisecond to as a unit for reaction time. First, we choose the first two columns in an Excel spreadsheet. Then the second column is the distance fallen y measured in millimeter, which decreases as it goes down from 750 millimeter to 0 millimeter. The first column is used for reaction time millisecond with d equals 0 millimeter. We type equals square root of 2 times 9.8, and we have to input the value for the distance fallen y here, and then all of them divided by 9.8 times 10 to the minus 3. The distance fallen y should be the relative box from the second column. The rest of the first column will be the same with the relative distance fallen y in milliseconds until we reach 0. This is an example of my Excel spreadsheet for the first two columns. The first RT strip with D equals 0 millimeter is actually not very accurate for short reaction times. With the first strip, reaction times that are shorter than 150 milliseconds are not very accurate because the times are very close together. However, we can improve this by letting RT strip to fall for a certain distance before the subject can see the strip and react to catch it. The longer we let the RT strip fall before the subject sees it, the more accurate the reaction time. With that said, 3 other RT strips were made. They are actually D equal 5 millimeter, which means we will let the strip fall for 5 millimeter before. D equal 10 millimeter, let the strip fall for 10, and then D equal 20 millimeter. So now we can make an improved RT strip. The middle column here is the distance fallen y millimeter will not change, and we will add a D equal 5 millimeter column in the third column of Excel next to this middle column, and that column is the reaction time of this column is actually calculated by this equation, which T is equal to square root of 2 times the sum of dy plus 5, and then all of them divided by 9.8 times 10 to the minus 3, and this first square root will minus the second square root, which is square root of 2 times 5 divided by 9.8 times 10 to the minus 3. The distance fallen increased for an addition of 5 millimeter. However, as we do not count the time the strip takes to fall for 5 millimeter as the reaction time of the subject, we have to subtract it from the total reaction time of the subject. And thus from that, we can enter this equation like this in Excel, and we can calculate the whole column for 5 millimeter. And just like that, we can use the same way to make another two strips for 10 millimeter, D equal 10 millimeter, and D equal 20 millimeter. The method to calculate those actually are the same as 5 millimeter, as the reaction time when the D is equal to 10 millimeter look like this, and the reaction time for D equal 20 millimeters look like this. And we will use this formula, we will enter this formula in Excel to calculate D equal 10, and this one for D equal 20 in Excel. This is what the arrangement of all of the strips on Excel will look like. Before printing the Excel sheet out, we have to make sure that each row height has to be 5 millimeter to correspond to the 5 millimeter drop increments. In order to do this, we first have to select row height from the Format menu in Excel to set the points for our font. The closest font to 5 millimeter should be 15. That's what I determine. We will have to print one page out first to see if each cell is really 5 millimeter, and then we will print the rest and cut it out. Next, a cardboard piece was prepared with the size of about 6 centimeter times 80 centimeter. The cardboard piece should be about 0.5 centimeter to 1 centimeter thick. The artist strip was printed out in sections in Excel, and then it was cut and taped to the cardboard. The artist strip has two sides. One side shows the D equals 0 millimeter and 5 millimeter, and the other side shows the 10 millimeter and the 20 millimeter with according reaction time in milliseconds. A sufficient large artist shield was also made from cardboard, which is used to prevent the subjects from seeing the strip dropping. On the shield, there should be horizontal lines show artist strip alignment relative to the artist shield. There are 4 different lines below and above for the D equals 0, 5, 10, and 20 millimeter. So now we can measure the reaction time. To measure a subject reaction time using the artist strip should have to initially prevent the subject from seeing the strip. The artist strip has to be held against the artist shield on the side facing away from the subject. The subject has to hold their finger just below the bottom edge of the artist shield and prepares to catch the artist strip after the experimenter lets it fall. The subject always has to hold their finger just below the bottom edge of the artist shield, and while the artist strip is held by the experimenter with its bottom at the appropriate mark for the different D. So this is my results. My data for 5 different subjects. The first one is Emma, and this is Emma reaction time when I use the D equals 0 millimeter strip, and her average reaction times is actually 808.5 milliseconds. The standard deviation is 5.85, and the accuracy is 73.2%. This is her reaction time for D equal 5 millimeter. The mean is 202.8, and this one is the average for D equal 10 millimeter. The same goes with D equal 10 millimeter with her average reaction times is 191.2, and for D equal 20, her reaction times is 167.7. As we can see, the relative accuracy is actually increasing as I use the D equal 10 millimeter and the D equal 20 millimeter. Her reaction times is actually below 150 milliseconds, but the accuracy is still increasing. So for the second subject, which is Ming Wing, this is her data, and for D equals 0 millimeter, her average reaction times is 190.9 milliseconds. For D equals 5, her reaction times is 141.6 milliseconds. For D equals 10 millimeter, her reaction times is 147.9 milliseconds. And for D equals 20, her reaction time is 155.9 milliseconds. And just like the first subject, Emma, her data is actually also increased in accuracy as I use the second and the third reaction strip, which is D equal 10 and D equal 20. The case is actually the same for the third, fourth, and the fourth subject. They actually also have the accuracy of the reaction time increasing when I use the second and I use the third and the fourth reaction strip to measure the reaction times. There's also a rare case where the first reaction strip, which is D equals 0, has a higher relative accuracy compared to the D equal 5 and D equal 10. But overall, the D equal 10 and D equal 20 all have the higher relative accuracy compared to the first two. All of the 5 subjects actually don't have a high standard deviation, which means their reaction times in the 10 times that I measure them is actually pretty consistent. So I can conclude that this data is trustful. Okay, so after we measured the reaction time of the 5 subjects in normal case, we can try to add some additional situations. The question is, how would the reaction meter readings be affected if the measurement was made in an elevator? The first case is the elevator is going up at a constant velocity of 5 milliseconds. If the elevator is going up at a constant velocity, it means that the net force acting on the elevator is equal to 0. And why the F equal ma, this means that the acceleration of the elevator is 0. So when we conduct the experiment in the elevator in this case, there will be no change to the reaction meter readings as the free fall of the RT strip and the RT shield will be like normal, with its acceleration relative to the Earth is 9.8 meters per second.